Okay, so we are discussing about this accelerometer, which is having like this kind of combs, and using some electronic circuit you can measure the change in the capacitance and can accordingly measure the output voltage, and this output voltage is related to the deflection or the movement of this proof mass and accordingly acceleration of the body. Now let us say we will see that how we can use this kind of capacitive measurement for force balance sensing. This is force balance sensing, means the force will be balanced. So what does that mean? We will see. So let us say that there is this proof mass which can move in the vertical direction only. Okay. So it can, this proof mass can oscillate in this direction, and these two plates A and B are fixed plates, in between which we are measuring capacitance between the proof mass and the A and also proof mass and the B. Okay. So initially both the top plate and bottom plate are at the same distance from the mass. So this is D, and the same from the same distance, and that distance is D, let us say. Now, so this is the complete circuit how we can get force balance. So that we will analyze one by one using like for this kind of capacitive accelerometer. So let us say we apply some voltage here, VA equals to V naught plus Vm sin omega t. So some AC signal I am applying with some DC bias, right. So this V0 is DC bias and Vm sin omega t, where Vm is the like the amplitude or the maximum value. So 2 Vm will be the peak to peak value, right, and omega is the frequency, and Vb on the another plate, like the bottom plate, we will use the same in magnitude. In the bottom plate we will use the same magnitude, but negative voltage. So this will be minus of V0 plus Vm sin omega t. Okay. Now if I consider this voltage to be let us say this voltage is Vi. So this voltage is Vi, and how much is the Vi? While the capacitor, while the mass is not moving, it is from the same, it is at the same distance from the top plate and bottom plate, then the capacitor for both the sides are same. So it will be like 0, because it is like plus V0 plus Vm sin omega t to minus V0 plus Vm sin omega t. And how these signals look like? If so, let us say if this is V naught, then if this is my Va, then the so if this is Va, then this is Vb, right. So this is, let us say, Va and this is Vb. So it is same in magnitude but opposite in sign. So it is same in magnitude but opposite in sign. So the Vi will be 0 initially, right. Now if the tip, if this mass moves, then the capacitor, like this distance will be different, and let us assume that it has moved towards the top by a distance x. So let us assume that it has moved to the top by an amount x. Okay. So the gap between the top plate and the mass is now d minus x, whereas the bottom plate and the mass, the proof mass is d plus x, right. Now if the voltage induced in the central mass is Vi, then the charge at the top plate, because of the top plate, will be Va minus Vi into C1, where C1 is the capacitance between this plate and C2 is the capacitance between this plate. Now the charge have to be conserved, right. It will be the same charge of the both side of the central mass. So Vi minus Vb into C2, and from there we can write that Vi is equal to C1 minus C2 divided by C1 plus C2 into V0 plus Vm sin omega t, okay, plus Vm sin omega t. Now here we have put that Va equals to V0 plus Vm sin omega t and Vb equals to minus of V0 plus Vm sin omega t, right. So this we have put and we will get this expression. Now this signal, okay, before we go there, so what is C1 minus C2 by C1 plus C2? So C1 equals to epsilon A by D1, and what is this D1? D1 is like epsilon A divided by D minus x, and C2 is epsilon A divided by D plus x, right, because this is the distance between the central mass and the top plate and bottom plate. Now if we calculate this, then C1 minus C2 by C1 plus C2 will get as, this term will give as x by d, x by d, where x is the displacement of the mass and d is the initial gap between the central mass and the top or bottom plate. Now once this signal pass through the capacitor, then capacitor blocks the DC, only the AC is passed through. So this signal, once it goes, then this V0 will get cut, because the capacitor will block this V0, the DC part, only the AC will go. So this, let us say this is at this point, if it is Vi, let us say V plus, which is going at the positive terminal, then we write that plus equals to so C1 minus C2 divided by C1 plus C2, we write x by d to Vm sin omega t, right. So this is capacitor blocks the DC, and now this signal is coming as like the V positive is x by d Vm sin omega t, and this is going through this operational amplifier which is connected as a buffer amplifier. So here also it will be same V plus, right, here also it will be same V plus. Then we are using a demodulator circuit which will actually kind of block the higher frequencies and only the lower frequencies will pass. It will be kind of used as an envelope detector, okay. So the outside, the output of the demodulator what we will get. So let us say this signal we call VFB. So that is feedback because it is again connected to the input side. So that is the feedback signal. So the V feedback or VFB will be equals to A1 Vm x by d. So where from this A1 is coming? A1 is coming because we are using here an amplifier which has a gain factor of A1. So that A1 will come, right? And what does this sin omega t go? So this omega usually we keep it higher frequency. So we choose the omega such that it is very high value, and then it gets blocked at the demodulator circuit. So only the AC part is there. Only the DC part or the magnitude part is there. Now if this X is already a time varying signal, then we will be able to detect that. So let us say this X itself as a like with time it is changing, right? So then feedback also will be like that. So it is not like that we are chopping off all the time varying signal, but it is only, we are only blocking the high frequency so that we can see exactly how the X is changing, right? How the X is changing with time. As the mass has moved to the like the upper side, now the distance between the top plate and the bottom plate is different, right? And because of that there is a charge imbalance, and because of that there is some electrostatic force. Now how much is that electrostatic force? So electrostatic normal force between two parallel plate can be written as like W by D, where because this is known to us, right, that W or the energy divided by the distance we usually gets the force, right. So like electric field is dV dr, or V is the potential or work done. Here also W by the distance. Now in this case what is the W? W is like the energy stored in the capacitor, and how much is that? That is half CV square. From electrostatics we know the energy stored is half CV square divided by D, and D is the distance between the two plates. So again C equals to epsilon A by D. So and then there is this V square, and because of this another D, so it will become D square, right, because 1 by D is coming from the C, and then already there was a D, so it is epsilon A by D square into V square, right. Okay. Now this is the force in between two parallel plate, like the normal force. Now in our case what will be that force? So that electrostatic force equals to A epsilon naught by 2, where A is the area of the like central mass as well as the top plate and bottom plate, it is all same, into V0 minus VFB divided by D minus x whole square minus of 0 plus VFB divided by D plus x whole square. So see here we are only taking V0 minus VFB or V0 plus VFB. Why is that? Because the Vm sin omega t with respect to the negative part, it was already in symmetry, like the central mass was already symmetrical, right, and while the mass has not moved, then at that time Vi was 0, because both the side capacitance is same, then the charges are same and the force is also same. So there was no net force in the vertical direction. But as this moved, then As this move, then what happened is there is a DC level shift, right? There is a DC level shift, and because of that this V0 minus VFB and V0 plus VFB is coming, because one side it is like plus V0 and other side is minus V0, and accordingly the distance also between the top plate and bottom plate is, one side it is d minus x and another side it is d plus x. So while the VFB is coming from the top side, it is V0 minus VFB, whereas for the bottom side it is minus V0 minus VFB, so it becomes V0 plus VFB, and both are these forces are opposite. So the net forces will be, we can simplify it to 2a epsilon naught V0 Vm A1 x by dq, and here we have considered that the deflection of the central mass is very small compared to the gap. So this is the electrostatic force. Now some this body or this sensor accelerometer has been kept on some body which is actually accelerating, and because of that this force has applied, right? So if the body is accelerating with an acceleration, let us say small a, then the force applied is, actual force applied is mass into acceleration, right, where mass is the, m is the mass of the sensor, of this central mass. This central mass is having a mass of m. So then the force is ma, and this force is equals to the electrostatic force, because it only has this amount of force only has been it's only able to move the proof mass to its top position or bottom position. So ma is equals to So now we can see that this x by d is directly proportional to the acceleration. So once we measure, once we know that how much is the deflection x, then we know that how much is the acceleration, because this d, m, capital A1, all these terms are already known to us. So now if we, I am telling this sentence again. So now we see that the x by d is equals to d square m into acceleration divided by all these constant terms, right? Now this acceleration, according to the acceleration, this x will change. So once we can measure the x, then we know that how much is the acceleration, and this d, m, capital A, epsilon naught, or this V0, Vm and A1, all these terms are already decided by us. So we are deciding, we know that what is the geometry we have designed for the sensor. So accordingly we know this area, mass and other things, the gap and all, and also we know that how much voltage we are applying. So these terms are also all known, and we measure the distance, and accordingly we can get the acceleration. Now how we can measure the distance, because we know that this is x by d, and this x by d is again related to VFB. So we know that how much is the this Vm we know, this A1 also we know, and accordingly we can calculate the x by t, because this feedback voltage what we are actually connecting to the input again as feedback, that we can measure here. So we can measure the feedback voltage from this point, and accordingly we can calculate what is my x by d, and accordingly we can calculate how much will be the acceleration. So in using this circuit we can use using this kind of system we can measure the acceleration. So with this we like finish this module as well as this course, and before ending, so we will just revisit once that what we have learnt in this course. So initially in this course we have first studied about, like we have seen, we have that what are MEMS sensors, what are microscale or nanoscale sensors, and why they are important, right? And then we have also discussed about the scaling effect, right? While you are already we are using some similar kind of sensors in macro scale, what does it like how does it change when we scale down to micro scale or nanoscale, and there we have seen that the physics remains same but the phenomena might change, because like some forces are dominant, like the volumetric forces are dominant in 3D scale, whereas like the surface forces are dominant in micro scale. What we have seen in scaling, that the volumetric forces are dominant in the macro scale, like in bigger scale, right? Whereas the surface forces or one dimensional forces are dominant in like micro scale or nano scale, and accordingly the phenomena changes. Then we have seen like the simple mechanics, and we have like how the force and deflection is related, and for measuring a force or any pressure or similar mass of some particular body, then we actually use some kind of moving structure like cantilever or membrane, and as it applies some kind of force, then the structure deflects, and accordingly we measure the deflection by electronic way or optical way, and accordingly we calculate the force. Now how this force and deflection are related for cantilever or for membrane, that we have already discussed in the module 1 and 2, and then we have also seen that for complicated structure, like if we have more than one beam, like 2 beams or 3 beams, then we can use the parallel like we can use the spring mass system, like 2 parallel spring or 2 springs in series, and can calculate the equivalent spring constant, and can accordingly calculate the force. Right. Then we have also then we have discussed about the coupled electromechanics, and there we have seen that how on a body we are applying both the electrostatic force and elastic force are applied together, and how they act together, and how the deflection changes with different kind of voltages, and what is pull-in voltage, and then stiction, and how this kind of cantilevers or membranes are made. We have learnt about silicon etching, then also some material deposition in very short way. We have discussed some material deposition, also very important lithography, like how do you make actually this kind of nano patterns, right? Whether you want to make a micro scale pattern or nanoscale pattern, how you can use like an e-beam, like a pen or a UV light for that purpose. And finally we have discussed 2 specific sensors, one is pressure sensor and another is accelerometer, and we have also seen how we can use this kind of system for measuring pressure and acceleration, and also we can mount it and in very small area, because these are also very small sizes, right? So this kind of pressure sensors or accelerometers are the product of MEMS technology. I hope you have enjoyed this course. Thank you.